Hello and welcome to the final part of Lesson 4. One of the things that we looked at in the previous part of this lesson was how molecular weight and structure affected the viscosity of polymer melts. What I'd like to do in this part of the lesson is to examine the effect of temperature on not only the viscosity of polymer melts, but on other material functions as well. What we're going to see is that it's possible to predict the temperature variation of material functions quite accurately from limited data. This is of great use to us when it comes to polymer processing operations. But rather than take my word for it, let's see why this approach is so valuable to us. So I'd like to frame this discussion around an extrusion line, maybe not unsurprisingly. So if we look at an extrusion line from a temperature standpoint, we can see there's lots of changes of temperature. Let's say we're extruding a linear low density polyethylene. We might along the extrusion barrel have a range of temperatures, I don't know, between 130, 150 degrees C, something like that. Coming into the die head, we might increase the temperature a little bit to drop the viscosity to make the pressure drops a little less, so we might increase the temperature to 160, maybe 170. Then we have our extrudate emerging and going into a quench bath, so we have a big temperature gradient potentially there, 160 to maybe 80 degrees, and then downstream we've got our processing equipment in terms of haul-offs and so forth. So really what we'd like to understand is, well, how does apparent viscosity change with temperature? Does our stress relaxation behaviour change with temperature? Does anything else change with behaviour that we need to know about? And so what we find is that yes, things do change with temperature, and yes, we can, to a reasonable extent, predict how that's going to happen. And so by means of an example, I'd like to show you a graph of the variation of apparent viscosity as a function of shear rate with temperature for a low density polythene. So there on the whiteboard is a plot of shear viscosity as a function of shear rate. The data that is on the board at the moment is for low density polythene at 513 Kelvin. And we can see that we've kind of got a Corot type behaviour here for our shear viscosity. We've got a low shear rate Newtonian plateau at around 2-ish, 3-ish times 10 to the 3 Pascal second, and that after about 1-ish reciprocal second we enter a shear thinning regime. If we drop the temperature, let's say we drop the temperature to 443 Kelvin, we still see a Corot-like behaviour, but our viscosities are now a lot higher, about an order of magnitude higher. If we drop the temperature once again, let's say to 388 Kelvin, we see the same kind of behaviour, as in we've still got a Corot type shear thinning response, but again, the absolute values of our shear viscosity have increased by about an order of magnitude. So there is a very strong temperature dependence on apparent viscosity with temperature. Now, what we'd like to be able to do is predict this behaviour. We'd like to predict this behaviour in an ideal way from very limited data. In the ideal world, can we just take one set of temperature data, maybe let's say at 500 Kelvin or 400 Kelvin, and then infer the full range of temperature-dependent behaviour for that polymer system? Because if we could, or estimate it to the accuracy that we need it to get the information that is good enough and fit for purpose, then that is absolutely ideal. So I'd like to introduce a technique to you called time-temperature superposition. And time-temperature superposition, or TTS, is applied to materials that are termed thermorheologically simple. And if you find in the literature TTS or values of various TTS parameters applied to the material that you're looking at, the chances are the material you're looking at is thermorheologically simple. We can define whether or not a novel material is thermorheologically simple by doing the sorts of experiments I'm about to talk about. Because for these materials, we should be able to obtain a single, what we term master curve, of what we call reduced viscosity as a function of reduced shear rate. So let me just define what I mean by those. So my reduced viscosity is my viscosity as a function of, let's say, shear rate and temperature, divided by a shift factor AT. We'll talk more about AT in a minute. My reduced shear rate is simply the product of that shift factor AT times the shear rate. And my shift factor AT can quite simply be estimated by the ratio of the low shear rate plateau viscosity at the temperature of interest divided by the low shear rate plateau viscosity at whatever temperature we designate to be a reference temperature. Okay, that is a bit of a simplification because strictly the relationship for my shift factor AT also involves the ratio of the reference temperatures and the ratio of the densities. But what we find is that that group of temperature and density information tends to equal roughly 1, whereas the ratio of the viscosities equal orders of magnitude of different from 1. So, to a first estimate, that's how we can estimate AT if we've got some experimental data. So, let's define a strategy as to how we're going to go about this. We're going to first of all choose a reference temperature. I'm going to do so relatively arbitrarily. For that reference temperature, I'm then going to calculate AT. So, for T0, my reference temperature AT is 1. For different temperatures, I can then calculate what AT is. So for those different temperatures, I'm then going to calculate what my reduced viscosity, my reduced shear rate is, and then I'm going to plot the master curve out. So if we've got experimental data for viscosity available at multiple temperatures, then we can directly calculate my shift factor AT. If we've got experimental data available over multiple temperatures, we may not need to do this approach anyway because we may have all the data that we need. So what happens if we haven't got those data? Are there methods available to us that allow us to calculate AT from either empirical routes or from theoretical routes such that we can infer this temperature dependent behavior without having to measure it all? And the answer is yes, you can. So if you are dealing with a polymeric system that doesn't have a glass transition temperature, there on the board is one way that you can calculate that shift factor AT. Now, it depends on a number of parameters. It depends on an activation energy, delta E. It depends on the universal gas constant, script R. And it also depends on the difference between the reciprocal of the temperature of interest and the reference temperature. What you can find in the literature are tables of values for those activation energies, which is really, really useful. So if we're dealing with low density polyethylene, for example, the activation energy will typically range between about 61 and 67 kilojoules per mole at 100 degrees C. So those are for non-glassy polymers. For glassy polymers, we've got a slightly different approach. We've got an equation called the Williams, Landel and Ferry equation, and that will give you an idea of the shift factor over the range between the glass transition temperature and, roughly speaking, 100 plus that glass transition temperature. We're working in Kelvin here. So the Williams-Landel-Ferry equation, or WLF equation, takes the form I've put on the board there. And again, in the literature, you can find WLF constants for all sorts of glassy polymers, for example, polyvinyl acetate or polymethyl methacrylate. If you've got a glassy polymer that you can't find shift factor data for, there's some universal values that I've put on the board there that you can use alongside an experimentally measured glass transition temperature with, for example, DSC. Okay, so now that we know this, let's go back to our low density polyethylene example and see if we can apply this new information. So remember, for our low density polyethylene example, we had 3 different temperatures and we had measurements of shear viscosity as a function of shear rate. So I'm going to arbitrarily choose my reference temperature for that system to be the lowest temperature. That was 388 Kelvin. If I look at the graph of the materials, I can find the low shear rate plateau viscosity at each of the different temperatures. And we can see on the board there that indeed at 388 Kelvin, I've got roughly 2 times 10 to the 5 pascal second. At the next temperature, 443 Kelvin, we've got around 2 times 10 to the 4 pascal second, an order of magnitude reduction. And then for our hottest temperature at 513 Kelvin, we've got yet another rough order of magnitude reduction in our low shear rate plateau viscosity. So for each of those temperatures, 388, 443, 513, I can now calculate my shift factor AT. And for the reference temperature is obviously 1. And then for the higher temperatures, we get low, decreasing shift factors. All right, so now I know my shift factors, I can plot out the reduced viscosity as a function of reduced shear rate, and I get the following graph. So low-density polyethylene is thermorheologically simple because I can plot a master curve of reduced viscosity as a function of reduced shear rate for 3 different temperatures that span roughly 130, 140 Kelvin. So this is really useful. So for any intermediate temperature now, I could quite easily work out what the temperature variation of viscosity is going to be as a function of shear rate. Very, very valuable indeed. Okay, so if we look at the values of those shift factors, each of those AT values, I can get some even more useful information. This graph here plots shift factor as a function of inverse temperature, 1 over T. And wow, look at that. They all are very nicely predicted by the activation energy method. So the red circles on this board are the calculated shift factors that we were using on the previous graph that I'd calculated knowing the temperatures. The blue dashed line there is the activation energy method using 58 kilojoules per mole of activation energy, which is quite close to that range of 61 to 67 for low density polyethylene. So we could just have one curve of viscosity as a function of shear rate at one temperature, use the activation energy method using 60 odd kilojoules per mole, and we would be able to get the entire spectrum of temperature dependence for shear viscosity as a function of shear rate. Very, very useful indeed. And it extends beyond just viscosity. So we also find that other material parameters can be related in this shift factor approach. We can calculate normal stress coefficients and shifted normal stress coefficients. Not only that, we can look at reduced elastic moduli and reduced viscous moduli, again, all using this shift factor approach. We can even combine this shift factor approach into generalized Newtonian fluid expressions. So, for example, there at the base of the board, I've put the Corot equation. Remember, the Corot equation describes a material that has a low shear rate Newtonian plateau and then shear thins away from that. We can substitute into that the shifted version of eta 0. So there we have in green on that new equation the shifted version of eta 0. And also we could calculate the shifted shear rate. So this whole idea of time temperature superposition is a very, very powerful one. It's a very, very useful one if we have access to limited data, because we can quickly infer what the temperature variation of key material parameters are going to be. And this can be incredibly useful if we haven't got the means on site to be able to measure them immediately. So let's summarize a few key points. Time temperature superposition is a very useful technique for thermorheologically simple materials. We saw how the viscosity data for low density polyethylene could collapse onto a single reduced viscosity master curve. We can predict the shift factors required for that collapse for polymers with and without a glass transition temperature. And we can apply the same technique to normal stress differences, to viscous and elastic moduli, and we can also substitute those results into constitutive equations that would then give us the viscosity variation as a function of shear rate and temperature for a given material.